So what is Mach's principle? Can you state it rigorously, or you can't, and that's the reason why it's unproved rigorously?
Well, as I say, Mach's principle is that the question is when we rotate ourselves, if we spin round, our arms flail out, or if we drive around a curve in the road, we kind of get pushed to the side of the car, and we say, that's caused by the centrifugal force or something like that. But that's just a label. And the question is, let's take the rotating case. What actually is it that that determines whether you're rotating or not rotating? And Mach, I mean, this actually goes back to Bishop Berkeley back, in the earlier times. But in the 19th century, Ernst Mach said, well, the reason why we say we're rotating is because when we rotate, we see the distant stars moving. And he said, well, that's not a coincidence. It's because of the kind of gravitational effect of the distant matter that defines what a non-rotating frame is and a rotating frame. And this was a very big inspiration for Einstein in his developing his theory of general relativity. And indeed, in general relativity, there is an effect called the Lenz-Turing effect, where if you have a massive shell, if you like, and you rotate it, that rotating mass drags the local frames of reference around with it. So in other words, locally, that tells you, whether you're rotating or not. Now, it then becomes a kind of, then you ask the question, does general relativity automatically is it internally consistent with Mach's principle? Well, you can have space-times where there is no distant matter. So the Schwarzschild solution for an isolated star or black hole doesn't have distant matter. But in some sense, you have to define then what you mean by rotating or non-rotating. In the case of a Schwarzschild, it's a non-rotating solution. You kind of have to impose that non-rotating condition by a boundary condition at infinity. But I think most cosmologists believe that in the real world, where we don't live in, the Earth is not an isolated mass in a otherwise empty universe. It's part of the universe, and I think most cosmologists would accept that Mach's principle probably is the key reason why we experience so-called inertial forces in rotating frames of reference, because these are the ones moving with respect to the distant stars. But it's hard to prove it because we don't yet know. We don't even know whether the universe is infinite or finite. We don't really know how much matter there is. So it's become I like to think of it like this. Mach's principle has become a little bit like some of these famous sort of conjectures in number theory, like Goldbach's conjecture, that every even number is a sum of two prime numbers. I mean, everybody kind of believes it's true, but nobody knows how to prove it. So it's not very high up in the research agenda because nobody knows how to prove it. And in a way, I think Mach's principle is similar. It's difficult to know how to prove it rigorously, but I think most cosmologists would sort of accept that it's something, there's some truth in it. And I think, as I say, I think that we've got to get to that sort of stage in thinking about quantum mechanics as well.
Okay, fill in this blank for me. Mach's principle is to general relativity as blank is to quantum mechanics.
Well, okay. I mean, I have my own, you're putting me on the spot. I mean, I have my own, ideas about quantum mechanics or quantum physics, let's say. And I've tried to propose, an idea which I call the cosmological invariant set postulate. And this is very much, motivated by chaos theory, that there are systems which exhibit this extraordinarily beautiful geometric structure in their state space. and that they, if you start them from an arbitrary initial condition and just leave them for a long time, eventually they just evolve on this what's called invariant set, or sometimes called an attractor. But these are fractal attractors. And my kind of principle, which would be consistent with what I'm talking about here, the holistic nature of quantum physics, would be the universe evolving on a cosmological invariant set. So Mach's principle is gravity as, perhaps this cosmological invariant set postulate is to quantum physics. And the reason for saying that is that it can explain some of these difficult issues like entanglement and Bell's theorem without having to invoke non-locality or indeterminism, all the sort of things that Einstein hated.
So, Professor, I'm a stickler for words, and I noticed a few times you were going to say that. Okay, so I have 3 questions here. Einstein's theory is consistent with Mach's principles. Then you corrected yourself and said is internally consistent with Mach's principle. So one of the questions I have is, well, what's the difference between being consistent and internally consistent? Okay, so we'll get to that, but just in a moment, so I don't forget. You corrected yourself when you were saying quantum mechanics, you switched it to quantum physics. So I'm curious what the difference is there that you see. And then another time is invariant sets, which is the same as a fractal attractor. Okay, if it's the same as a fractal attractor, why did you rename it as invariant set? Okay, so those are 3 questions. The first one was about internal consistency versus consistency.
Okay, on the first question, there are solutions of Einstein's equations. And I mentioned earlier the isolated body and the Schwarzschild solution. Another one is what's called de Sitter space, which has no matter in it, and yet space is curved. It's curved by the cosmological constant. So you can come up with space times which satisfy Einstein's field equations, which are not Machian, because there's no distant matter for them to be. However, what I'm saying is, the real world, forget what I actually said, because what I'm trying to say is the real world, which is governed by, let's say, to a good approximation, one of the Friedman-Robertson-Walker solutions, the cosmological solutions of Einstein's equations, is consistent with Mach's principle. So not all solutions of Einstein's field equations are consistent with Mach's principle, but the Friedman type of equations are. And we live in a Friedman type of universe. That is we don't live in de Sitter space, and we don't live in an isolated Schwarzschild space. We live in something which, at least on the very, very, very large scale, approximates quite well to the Friedman and Robertson-Walker cosmology. So from that point of view, that's consistent with Mach's principle.
Quantum physics versus mechanics.
Yeah, no, quantum mechanics is a very specific theory. It's the theory that Heisenberg first proposed almost 100 years ago, next year, I guess, and then Schrödinger very shortly afterwards with his wave mechanics version. So that's what we mean by quantum mechanics. It's a specific theory of quantum phenomena. But I use the word quantum physics in a slightly more generic way, which is, the set of all observations of the world, involving atoms and particles and entangled systems, where maybe quantum mechanics isn't the final word. I mean, that would be my belief, that it's not the final answer to how to describe quantum physics in as accurate a way as possible.
I see. Okay, now the third one was invariant sets versus a fractal attractor.
Yeah, well, the concept of an attractor is that if you start with any old initial condition, and you run your differential equations forward in time, and just leave it for, a very, very, very long time, then the state gets attracted to this special fractal. But the hypothesis I want to put forward is that the universe has always been evolving on this geometry. So it's never been attracted towards it. It was always on it, and it always will be on it, potentially, for an infinite time in the past or a finite time in the future. It might end up being cyclical. It might end up repeating itself at some stage. But the point is, I'm not invoking the concept of it being attracted, the states of the universe being attracted towards this geometry, but it's just, this is the geometry that it evolves on. And the concept behind this geometry is that it's called an invariant set, because if you're on it today, you always will be on it in the future, and you always have been on it in the past. So the set is, in some sense, or the geometry is invariant under time evolution. It's invariant under the propagating forwards or indeed backwards in time. So calling it an attractor, I don't like using that word, because it implies that I'm thinking about states. Yeah, you see, the point is, if you're outside it, you're violating, and this is an important point of my reason for believing why this is important for Bell's theorem. If you don't lie on the attractor, you're inconsistent with this basic postulate. The states which don't lie on the invariant set, by definition, don't satisfy the postulate that states of the world evolve on the invariant set. So the concept of being attracted towards it is not really a useful idea in this respect.
I see. So in other words, the invariant set is the attractor, but
Yes.
Our states are always on it?
Exactly. That's exactly right. The invariant set is the attractor, and states are on it. They always will be. They always have been. And any hypothetical, this is the point. If you imagine a counterfactual world, a hypothetical world in your head, where you've slightly changed, you've slightly moved the position of that chair, hypothetically, you haven't actually moved it, but you say, well, maybe I might have moved it. You've invented a counterfactual world, which doesn't really exist. It's a hypothetical world. Now, if that hypothetical world, if you've nudged the state of the universe off this invariant set, when you, in formulating such a hypothetical world, then I would say, that's inconsistent with the laws of physics, as I myself see.
So
them.
you may as well have said, what if this ball lifted up into the air? Like a counterfactual such as moving this chair a nudge that takes you off the attractor set or the invariant set,
right,
is equivalent to saying, what if there was some elephant that just appeared here? But even in that case, there is some quantum mechanical chance that an elephant can appear here. It's just minute.
Well, there's a quantum mechanical chance that of course, there is a chance an elephant might walk into this room, right, in 5 seconds. Who knows? I don't know. It's always possible. Shall we wait and see? No, didn't happen. Anyway, but it could have happened. But that's not quite the point I'm making. The point I'm making is, if we took the world as it was 20 seconds ago and said, okay, no elephant walked into the room 20 seconds ago, but is a world where everything was the same, you and me talking, the people in London doing their shopping, the Earth going around the sun going around the Milky Way, everything the same, except that an elephant walks into the room. Is that hypothetical world? Because it is hypothetical. It's not an actual world, because the elephant didn't walk in the room, right? It's just maybe we're hypothesizing the possibility that everything stayed the same, but an elephant walked in the room. What I'm saying is, if that hypothetical state does not lie on this invariant set, and I'm not saying that it does or it doesn't, but if it didn't, then that would not be consistent with the way I formulate the laws of physics.
If you enjoyed this toe clipping, then the full video is linked in the description. You should also sign up for Toe Mail, which is again in the description and the pinned comment. You'll receive immediate access to all exclusive updates from the Theories of Everything podcast. It also helps me communicate directly with the core toe community. You'll also receive my top 10 toes. Think of it as the intellectual version of Quentin Tarantino's Obsession.